Swayam Prabha. Digital India. Educated India.
So this was the last talk in the session. Now we will be having a keynote lecture by Professor Jeong Yeon. He's there. So it's going to be in virtual mode. Hello, Professor Yuan. Can you hear us?
Good morning.
Good morning.
Can you hear me well?
Yes, you are audible. Okay. So he will be giving a talk on robust decision making for the process industry and the complex manufacturing environment. Very warm welcome, Professor Yuan, to this session. We have audience in person as well as online for you to hear. Before beginning, I'll just give a brief bio of yourself to introduce you to the audience, and then you can begin on. So, Dr. Yan joined the Department of Chemical Engineering at Tsinghua University as an assistant professor in 2016. Before joining Tsinghua, he subsequently worked as a postdoctoral researcher at CMU and Auburn University. Promoted by smart manufacturing and clean energy manufacturing, the research directions of Dr. Yuan's group center on a fundamental understanding, theoretical development, and practical application of key issues in the areas of machine learning and optimization for decision making under uncertainty, autonomous optimization and control for modern manufacturing, and multi-skill process design, synthesis, and innovation towards carbon neutrality. During the past 5 years, Dr. Yuan has published several scientific papers in Computers and Chemical Engineering, AICHE Journal, IECR, and so on. He also has served as a chair and co-chair for several scientific sessions of the AICHE annual meeting, International Symposium on PSC, and European Symposium on Computer-Aided Process Engineering. So with this, I would hand over the session to Professor Yuan. Please take on.
Okay, thank you very much for your kind introduction. So, good morning, everybody. It's my great pleasure to have this opportunity to present our recent work on the robust decision making for the process industry, actually for the petrochemical industry on the complex manufacturing uncertainty. As everybody knows, continuous technology progress, the efficiency rates as well as the development of advanced technology infrastructure is going to accelerate the adoption of the next generation of advanced manufacturing technologies. So needless to say, as these technologies, including the decision-making listed in this figure, are referred to as Industry 4.0. which, as expected, has the potential to make companies more innovative, responsive, and cost-effective, efficient. As aforementioned, the decision-making is one of vital enabling technologies for the industry to not only to cope with the requirements from Industry 4.0, but also to help accelerate or achieve carbon neutrality. If we carefully check the life cycle of process industry, taking petrochemical industry as example, each step, I would say, will need the specific smart decisions, such as the inventory routing for the crude oil as well as the final products. The operational planning for production as well. Also, we need the scheduling for operational tasks. So each specific decision-making problem may share two common challenges. Number one is optimization model. The number two is the solution methods for the specifically the task, as well as, for example, the planning, scheduling, and the inventory routing. So when we mentioned the decision-making, this is during past several decades have got sufficient attention from industry and academia. The various state-of-the-art decision-making approaches have been pursued, such as the PIMS from Aspen and the ORIN for the scheduling. So, however, those classical approaches can't effectively cope with the increasing requirements, as I mentioned before. So, for example, if we mentioned the operational planning, so classical approaches for traditional rely on delta-based model for processing units, traditional is a linear. And so the mixed integer from the linear programming model can be formulated. So last one is without any detailed considerations on uncertainties. So although on the first day of this event, Rex and Marianti emphasized the importance of uncertainty. Here, in my talk, I will emphasize also later. So in this talk, based on the past lessons and experience, so in this talk, key issues following as follows will be tapped. The number one is balance the model accuracy and the computational expense. Number two is incorporate multi-scale models for different levels of decision making. The last one is handle the uncertainties to improve the robustness. So, okay, so why we should consider uncertainty? So answer can be clearly checked from the past 3-year pandemic as well as Russia-Ukraine conflict. Particularly the Russia-Ukraine conflict puts the negative effects on the Euro chemical industry. We should, that is to say, we should pursue smart optimization models and the cross-pointed solution algorithms to obtain optimal but flexible decisions. It is very important to revisit how to enrich the theorem of optimization under uncertainties, including the robust optimization, stochastic programming, and the chance constraint programming. And also they achieve the real world process industry applications. It should point out here that very recent years, the new approach named the distributional robust optimization, which combines the matrix law, stochastic programming, and the robust optimization, has gained increased attention. So based on this state-of-the-art optimization uncertainty methods, so in this talk, the following slides will focus on these 3 examples. The number one is use the traditional robust optimization for refinery-wide side under uncertainty. The second one is adjustable robust optimization for the integrated refinery and the petrochemical site. The last one is distributional robust optimization for maritime inventory routing of the refined diesels. So, okay, now let's move the first example. As everybody knows, the operational planning for refinery is not a new topic, all right? As illustrated by this figure, refinery is in charge of converting different kinds of crude oil into various wearable products. So as listed on the right side of these slides, so the aim is to maximize the profit following reasonable assumptions and simplifications. In general, the refinery planning operations problem mainly focuses on the selection of the processed crude oils, operational modes for the multi-modal units, for example, catalytic reforming. Also, it will decide the type or the selection of the final product, as well as the amount and property. So, as I mentioned before, so this is not a new topic here. When we model the processing units, now let's first look at the model of the crude oil distillate column. The swing cut technology is a state-of-the-art efficient approach to get the relationship between the pseudo component as well as the TBP temperature. That is to say, based on the TBB temperature, you can calculate the relevant yield for the pseudo components. So right, it also contains the yield constraints as well as the binary constraints to select the operation mode as well as the type low crude oil. So now let's move to the model for secondary processing units, including, for example, the fluid catalytic cracking as well as hydrogen treating. So this, I would say, this part is one of the most significant difference with the existing contributions, because we have plentiful industrial data sets. Instead of using the black box neural network, here we pursue an efficient approach to build the nonlinear surrogate model, as well as here. So that is to say, in order to improve the following computational efficiency, we use the bilinear quadratic linear term to formulate an explicit nonlinear model following the polynomial format. So the central matrix of this approach can be shown by this figure. All right. The first one is, as I mentioned, to define a large set of potential basic functions. Then we follow the model reduction idea to use mixed integer linear programming to optimally select the optimal the terms as well as the corresponding coefficient. So the right lower table figure just provides the example of the yield prediction for light products from the FCC, that is the catalytic cracking. So it should point out that following this approach, we can connect the yield as well as operational conditions. That is to say, unlike the traditional approach where the yield is fixed, here the yield is a variable. But I would emphasize that the nonlinear data drawing explicit models of a secondary process unit promote the overall planning model as a non-convex MILP formulation. I think I would say this is a barrier for the efficient approach development. So for other processing units, for example, the blending models and the product blending models can be briefly expressed here. So here the property is assumed to be the blended linear on volume basis. Okay. So based on the above mentioned mathematical model here, now one of our approach is to use robust optimization to deal uncertainties. In our work, the demand uncertainty is represented by box set. Here is an illustration figure of box set. Okay, so also the second uncertainty factor that is considered in our work is the price uncertainty. It is represented by box and ellipsoidal set. So why we use ellipsoidal and the box to represent the price uncertainty set? The reason is that for each product, uncertainty sale price has a upper bound and a lower bound. The interval set is used to demonstrate the bounds of uncertainty parameter. Instead, the price the price of different products may affect each other. To model this relationship, the ellipsoidal set for the uncertainty is there introduced. So as aforementioned, the introduction of nonlinear surrogate model caused the operational planning model as a non-convex MILP formulation, particularly the non-convex bilinear term. So to hedge against this barrier, so in our work, we introduced the enhanced normalized multiparametric discretion technology, namely ENMDT, to handle these problems. Because it can reduce the number of auxiliary variables that control the size. scale of the relaxed subproblem with desirable precision. So here, just give the overall flow sheet for how to use this approach to relax the bilinear term. Okay, so once we get the main problem is that because we introduce the bilinear, we then use the EAMDT to tackle this problem. So here we formulate the totally the proposed approach to solve the non-convex mixed integer nonlinear program. Here we combine the ENMDT and the OBBT, the optimality-based bound tightity, to accelerate the solution of the formulated problem. So in this framework, OBBT is implemented through solving the minimum or maximum problem with the current solution included for each variable to accelerate the overall convergence. So indeed, the relaxed convex MILP subproblem is solved to update the overall upper bound. The reduced NLP model is generated by fixing the binary variables and then solved to obtain the overall lower bound. The OBBT is implemented if necessary to renew the bounds for the variables included in the bilinear term. The iteration is then repeated until the termination criteria is met. And the final lower bound is regarded as the final optimal solution. Okay. So because this project is in cooperation with Sinopec, actually one of the largest petrochemical companies in China, around the world. Here is in order to systematically investigate the efficiency of the formulated mathematical model and the solution approach, the 5 types of mathematical model are carried out. So here, the deterministic linear model is just follow the PIMS, where the yield for each unit is fixed. The second one is a deterministic nonlinear model without any considerations of uncertainties. So model 1, model 2, model 3 is carried out to consider the demand, consider the price, and consider both demand and price on the uncertain issues. So clearly, from this figure, we can find that compared with the deterministic MILP model, the MILP model has much fewer variables and constraints since the yields, as I mentioned, are fixed. So model 1 is a similar formulation of demand inequalities, so that the number of those constraints and variables remains the same when compared with the deterministic MILP model. The combined interval and the ellipsoidal set for price uncertain adds some extra constraints and variables to the deterministic problem. According to this table, considering uncertainty through robust optimization, actually through the traditional robust optimization doesn't significantly increase the problem size when compared with the deterministic model. So here, based on the table, this table provides a detailed computational performance for addressing 3 cases under all uncertain scenarios using the commercial solver. It's a Baron, okay, as well as NMDT relaxed based global optimization approach and the proposed global optimization approach. Clearly, Baron can obtain the best solution for certain models with a gap less than, I would say, 0.01% at the cost of much more time when compared with the proposed algorithms. For the majority portion of the examples, Baron fails to narrow the gap within 10% with a reasonable computational time. On the other hand, the NMDT-based optimization framework provides a lower gap when compared to Baron for the certain models, but it typically reaches the defined maximum computational time. Here, you can approach this is all the touch upon the upper bound of the computational time. So On the middle part of this table, now a proposed approach, the algorithms can successfully solve the problem to the reasonable gap within the reasonable computational time. Okay, so that is to say, a tight gap optimum and less computational expense required by EMDT-based optimization framework can be achieved. So if this slide takes the robust counterpart on the demand and price uncertainty as example, here just shows the convergence curve and optimality gap following the execution time of the proposed algorithm and AMDT-based approaches respectively. All right. So from these figures, it can be found that the gap doesn't change significantly after the first 2,000 seconds. There exists a longer time interval between the lower bound and the upper bound. The main reason is that the OBBT is implemented for each variable included in the bilinear term after the first iteration. When the OBBT is applied, the new upper bound and optimality gap decrease quickly as the contraction of the variable bound reduce the same search reach. So these three figures just as well as the following tables just simply provide the influence of the demand uncertainty on the overall economic performance for all the three investigated cases. Clearly, consider demand uncertainty not only affects the choice of the feedstock, but also the operational modes. So this is just the brief introduction of the first project. After we finished this project, the senior packer asked us whether we can to further reduce or to further carefully consider the uncertainty while tackle the larger problem. For example, the integration of refinery, the integrated refinery petrochemical site. So this is the second topic. So as everybody knows, through the integration of refinery and petrochemical sites, streams of those low volume products such as, for example, benzene and propane are delivered to the downstream petrochemical processing units to produce higher valuable chemical products. Additionally, several intermediate streams, including the naphtha and gas oil, can be treated as a feedstock for ethylene cracking system, which can be regarded as a core part for the petrochemical site. With the intermediates and pursued raw materials, high-value chemical products such as polypropylene, polyethylene, and ethylene oxide can be obtained through a series of reaction and separation operations. Additionally, at the petrochemical site, the different polymer grades are considered in the planning operation. So furthermore, some intermediates from the downstream petrochemical sites can be recycled to upstream refinery site. In summary, through the integration of the refinery and the petrochemical site, the overall profit can be increased by reducing the cost of feedstock and making full use of the resources. The investigated integrated site actually is one of the largest facilities in China now. So the refinery site contains more than 24 main processing units, while the downstream petrochemical site contains more than 15 processing units. So this table just lists the main products that are considered in this work. Similarly to the first example, here is the key issue is to maximize the overall profit. Here and as shown in the right part of this slide. So, as I mentioned before, the assumptions and simplifications are as similar as the first example. I don't want to spend much time discussion the mathematical formulation. Here is the CDU formulation. Is actually is the same as the first example. So here, because of this project, is actually is an ongoing one, it's not has not been finished. So the current step is we just because of the very large scale problem. In this example, the yield for secondary processing units is considered as a constant related to the operation model. The second one is only one operation model can be used at each time period. The third one is the property is regarded as a constant related to the operation model. All right. So here is modeling following the simplified illustration of the excellent cracking system. There are 9 cracker funnels handling the feedstock. The intermediates from refinery site are first blended in tanks and then assigned to the funnels for deep cracking. The funnels are divided into 3 types based on the kind of the feedstock. The acid cracking comprises complex reactions, as everybody knows, that would add huge extra nonlinearity to the planning model when a rigorous kinetic reaction mechanism is incorporated. Modified models have been constructed to predict the yields of desired products, considering the operation condition and the cooking reaction. With the ethylene cracking system, the changeover of the feedstocks to each furnace is a key operation in determining the planning operation procedure. On the basis of a steady state, a linearized model is implemented to calculate the relative yield of the outlet products. Now let's move to the polymerization process. Several kinds of products can be obtained in one polymerization product unit. As examples, the polypropylene home polymer, the polypropylene radical copolymer, as well as the polypropylene impact copolymer are obtained from the polypropylene polymerization unit. Furthermore, it is assumed that there are 3 potential polymer grades to be selected for each polymer at each time period. Various grades need to be appointed when making decisions. Notice that 2 binary variables are introduced respectively to represent the allocation of specific product grade from polymer production unit and the changeover of the grades of the same product between adjunct time period. The changeover is further included in the objective function to represent the operation condition cost. So here are some additional constraints for enrich the mixed integer nonlinear programming formulation. So to be honest, the traditional robust optimization sometimes will generate much conservative results. In this example, uncertain product demand and, for example, and crude price will be involved to optimize the enterprise-wide strategy under a condition of complexity global competition. So in many practical problems, the decisions can be divided into 2 types. The number is non-adjustable variables. For example, is here and now decisions. And the second one is the wait and see, namely adjustable decisions. So the here and now decisions are usually related to the non-adjustable variables that can be determined before the realization of an uncertain parameter. So the wait and see decisions related to adjustable variables whose values are assigned after the realization of some uncertain parameters. So here we therefore adopt adjustable robust optimization to handle uncertain factors. Notice that since the decision rules is of unknown and complex, so here we use the linear affine decision rule to restrict the adjustable wait and see variables through non-adjustable here and now variables. So in general, compared to the traditional robust optimization, adjusted robust optimization reduce the conservative to some extent by implementing the aforementioned linear affine decision rule. So furthermore, in this work, before we further processing the uncertainty set, in our work, the demand uncertainty is denoted by a polyhedral set, unlike the first example. Here, just provides the illustration figure of polyhedral set. So, based on the, in order to further reduce the conservative caused by robust optimization, here we develop a dynamic uncertainty set based on the multi-parametric characterizations. So, what is the trick? The trick is that in real-world applications, the demands for products are usually determined based on the historical data in providing, when making decisions. So the question is, can we use the historical data to predict the upper bound and the lower bound of the uncertainty set? That is to say, can we further reduce or narrow the region uncertainty set following the execution time? So this is a key idea. So in traditionally, for multi-parametric problem, we can let the uncertainty set of phi t depends on the realization of uncertainties before t. That is, the uncertainty set is not fixed, but it is a variable. All right. So here is some statistics or mathematical formulation. So we just consider the short term as well as the medium term. This table just shows that each case, the scale increases with time horizon. The SRO means the traditional static robust optimization don't add extra variables or constraints to the original deterministic for problems, while the introduction of ARO, that is adjustable robust optimization, and or ARO with a dynamic uncertainty set, extend the model size through the definition of new decision variables and the corresponding constraints. However, the number of binary variables remains the same for the same time horizon problem, no matter which reformulation is adopted. An analyzer of the detailed distribution of the numbers of variables and constraints for the refinery and the petrochemical site reviews that the two subproblems have similar numbers of variables and the constraints, while the number of binary variables for the petrochemical site is nearly, you can find that here, nearly 3 times that for the refinery. So we first check the benefits of integrating upstream refinery and downstream petrochemical site under the deterministic scenario, and the results are presented in the lower table. You can find that the solution is obtained by solving the subproblems iteratively from the refinery to the petrochemical site, or from the petrochemical site to the refinery site, based on the deterministic model, as illustrated following the upper figure. In the hierarchical the approach, you can find that so the larger portion of the examples is infeasible. All right. So as shown in the lower table, the only feasible solution appears for the short term when the problem is solved iteratively from the refinery to the petrochemical cycle. Additionally, when adding the constraints from the refinery side, the petrochemical side converges to a suboptimal objective related to the results obtained for the subsequent load from the petrochemical site to the refinery. So now let's move to the effectiveness of the optimization under uncertainty here. The overall computational results are represented here. I should say that because of the ongoing static, here we just only use Baron to solve these problems. So in the case of the short term, the models are solved to the optimality gap of 1% within 9,000 seconds, except the ARO with dynamic uncertainty set model, which while a gap below 1.06% is reached in predefined maximum time. So in the other cases, the computational expense increases the expanded time horizon. The final operator gaps for these models exceeded the predefined 1% because along with the increasing number of constraints and variables, the number of bilinear terms increases, and the model thus becomes more complex to solve. So now we also develop the new algorithms instead of Byron to solve these very large scale problems. So a comparison with the hierarchical approach in terms of the overall objectives reveals that the integrated model provides a higher profit margin. In each case, for the same time horizon, the deterministic model yields a higher profit over the other models as the deterministic model targets at the nominal point. All right. With the introduction of robust optimization and a dynamic uncertainty set, is expected final product profit decrease to guarantee the feasibility over the entire uncertainty set. A comparison of the final objective values shows that the static robust optimization is the most conservative formulation. As can be seen, it enjoys the largest decrease in profit. So this just shows the benefit of introduce adjustable robust optimization, but also check the benefits of introducing the dynamic uncertainty set here, for no matter for the short term, but also for the medium term. The results from the adjustable robust optimization with dynamic uncertainty set has the lowest decrease when compared to SRO and the traditional ARO. So here we can also get the inventory level of crude oils for short-term case. We also can get the sale amounts of refined products as well as the petrochemical products in short term along the period. We can also get the for the medium term here showing this slide. So the final one is the planning operation for scheduling, because we integrated the scheduling as well as the planning. So we can check this Gantt chart to check the planning of feedstocks to cracking furnace for short term as well as the medium term. Also, we can check the planning operations in polymerization process for short term cases. So the final one is this slide just provides the objective values for some of the scenarios to check the robustness of the proposed optimization approach on the uncertainty. Here, from these two figures, we can check, we can conclude these following four results. The number one is ARO provides a closed solution to ARO with dynamic uncertainty set. The static robust optimization, actually the traditional robust optimization, produce the highest profit for the minimum objective here, objective value. The third one is the deterministic model fluctuated more drastically among the scenarios than those of the other models. The last one is static. Actually, the traditional robust provides a stable results. Here you can check this line. It's much more stable when compared to other curves. Actually, these curves are not satisfactory. So the last example, I will briefly to go through this. The last example, it actually is also an ongoing project in collaboration with PetroChina, following the two-stage distributional robust optimization for maritime inventory routing. So this project, I will say, I will
Professor Yuan,
save sometimes.
can you hear us? Sorry to interrupt you in between, but we just finished on time, 11:20. So could you please conclude as quickly as possible?
Okay, so I will quickly go through the final example. This example just follows the maritime transportation for reduced refined diesel along the east coast of China. So So from the north eastern part of Dalian to the following 20 cities. So the reason why we considered the alternate times because of the temporary shutdown reports, as well as the public emergencies, strong wind, unexpected surge fog. So the reason is the final objective is to minimize the total cost through decide the routing of each vessel, the number of port widths, as well as the loading low or uploading quantities at each port, as well as the final inventory. So here we just follow the two-stage worst-extent distributional vast optimization to deal with uncertainties. Actually, is the sailing time and waiting time at ports. So here we just follow the continuous time arc flow maritime inventory routing model to describe the deterministic model. It contains here is objective function, the routing constraints, as well as the loading and uploading constraints, scheduling constraints, inventory constraints. All right, because of the very large scale problem, as can be seen later, we propose banners decomposition approaches, where we use the independent MW cuts. Also, we use the multi-cut decomposition bands to solve the problem with optimal cuts. All right. The final is we also consider the high density cuts, relaxed accuracy during the two sub problems. So I would say we just to point out that here the two-stage distributional robust model on the uncertain waiting times contains more than 4 million variables, among which more than 100,000 are binary variables. So here the scheduling horizon is 720 hours. Here is the results. So I would also emphasize that the commercial solvers can't get the optimal solutions. Even now, proposed solutions can get the final results through more than 4 hours. Okay, this is a very, very large problem. This is just go through quickly. So here we also check the outer load sample performance of the two-stage distribution robust. So compared with the two-stage stochastic programming, the proposed the optimization uncertainty model provides better outer load sample performance compared to the two-stage stochastic programming, because two-stage stochastic programming provides higher average cost and worst case cost has much larger studied deviation. You can find it here. So also the final slides is here. So we can, through solving the problem, we can get the routing decisions on the uncertainty waiting times, but also we can follow in the uncertainties happened in sailing time. So here also we can get the Gantt chart of the two-stage distribution robust optimization in worst case and the best case. So each figure can provide the valuable guidelines for for decisions. So sorry for the extra time. So here is some concluding remarks. The number one is we develop a strategy to combine the global optimization and robust optimization to solve the uncertainty in the traditional refinery site. Also, we propose the dynamic uncertainty set based adjustable robust optimization to deal with the uncertainties arising from the integrated refinery and the petrochemical site. The last one is we propose a two-stage distribution robust optimization formulation coupled with tailored banners decomposition to handle uncertain sailing and waiting times for refined diesel. So this is my all the conclusions. So thank you very much, and I'm very sorry for the extra time. Thank you.
Thank you, Mr. Yuan, for a wonderful talk on this enterprise-wide optimization techniques and solution methods. So any questions from audience? We can take one brief question if anyone has. Yeah.
Thank you, Professor. This is Nitin from IIT Patna. So my question is that in one slide you have shown that the answer in your initial work you have shown that the number of variables and number of constraints are not changing while including the robust optimization. It is almost same for the MINLP. So, okay. In one slide, Professor, I have seen that the number of variables and number of constraints are not changing. So I am surprised to see that why they are not changing. It is same as for MINLP. Uh,
So, okay, thank you very much for your question. So I think because the very echo of the conference rooms is too loud to hear very well. So I can try my best to interpret your problem. You mentioned that the initial points for solving the problem.
I think the question is not very clear to Professor Yuan. Are you asking about the model? Which model the question has been asked on? I think.
So I'm really sorry. I can't hear you. Can't hear you very well. Before I don't know.
Okay,
It's
no
so loud. I
problem, no
cannot hear
problem,
you very well.
Professor Yuan. So, Dr. Dutt can connect with you over email or after this session. And in the interest of time, I would like to end this session here by giving a warm thanks to Professor Yuan and all the members who have attended this session. So, thank you very much, all of you, and we could proceed to the next sessions. Thank you, Mr. Yuan, for your time, and audience can connect to you over emails after this session for any questions.
Okay, thank you.
Okay, thank you. Yeah.